last class we had started our discussion on back-end design process in the entire cycle of VLSI design. Now, today we will be starting by looking at one of the first steps that is involved in the back-end design phase, and that is circuit or system partitioning. So, basically partitioning is one of the first stages that we need to carry out when we go about doing a physical layout or physical design of the system we want to map into silicon or any other target concept. So, first let us try to understand what are the different goals of partitioning, what does this partitioning problem involve. Broadly speaking, partitioning can be carried out at any level. So, here whatever I will be discussing today, this is applicable to system level partitioning, circuit level partitioning, even net level partitioning at a very low level. So, means where the netlist may comprise of transistors. So, we say that we have a system design, this can be a design at any level as input, which is some kind of a netlist. So, our goal of partitioning is to decompose this particular system, which is supposedly a complex one, a large one, into smaller subsystems. This is the simplest way of specifying the goal of partitioning. Given a bigger system, we have to break it up into smaller subsystems. Now, the reason we do this partitioning is that each such subsystem can be processed independently. Well, here we are saying designed, it depends on the context under which we are doing partitioning. So, each such subsystem can be handled independently, so that we have some kind of parallelism with respect to the thread of activities. So, after this partitioning is over. So, one goal of partitioning is also to achieve some degree of parallelism beyond a certain point. And obviously, this partitioning cannot be done in any arbitrary way. There will be some desirable properties that need to be looked at. One is of course to minimize the number of interconnections that cross the subsystems. So, we have to design, say, a bigger system, I break it up into two subsystems. It must be such that the number of lines crossing the partition is minimized. That will be called a good partition, and it depends on exactly what is the size of the target partitions we are looking at. So, we may have to do this kind of partitioning hierarchically till each subsystem that we get is of manageable size. So, after this process of partitioning is over, what we will be getting? We will be getting a set of smaller modules and some information regarding the interfaces. Interfaces means how these modules are interconnected among themselves, so some information regarding that. So, after the partitioning process is over, we have a set of modules and some information regarding how these modules are interconnected. Fine. So, let us take a very simple example. This is a gate level netlist. Of course, the gates are very small. I am not sure whether we will be able to see it very clearly. This diagram out here shows a gate level netlist on top. This gate level netlist we are partitioning like this, say this is one partition, this is another partition. Given a netlist like this, suppose we want to divide it into three parts. This is one partition we are showing out here. For this partition, the number of lines which are crossing the partition, the cut 1, this is cut 1 and this is cut 2, these are 4 each. So, there are only 4 interconnecting lines which are crossing the partitions, and moreover the sizes of the partitions are more or less equal. So, this will be called a good partition, right. So, this is just an example. So, this partition, as I told you earlier, this may be carried out at any level, not necessarily in the level of gates. So, there the basic building blocks may be higher level blocks as well, cells. Okay. So, before we talk about ways of doing partitioning, ways of estimating the cost of a partition, say with respect to the size of the cut, there are a few other things you need to understand and consider. The idea is that this process of partitioning that we are talking about, this can be done at several different levels. Like, say you can do partitioning at a very high level, which we call the level of the system level partitioning. Well, we can do partitioning at the level of boards, the printed circuit boards, board level partitioning, and we can even do partitioning at the level of chips. These are called chip level partitioning. Okay. So, actually when we do partitioning at the different levels, we need to look at the cost involved, because whether we are doing partitioning at the system level, board level or chip level, the cost of partitioning will vary. This will be having a very rough idea. Suppose we have a chip, this is a chip, and suppose we have a netlist which is supposed to be mapped within the chip itself, and if we do a partitioning at that level, so we are partitioning the circuit into 2 sub circuits which will be finally mapped inside the same chip. So, the cost of intra-chip partitioning, let us say some parameter x, but if the partitioning is such that a part of the circuit goes into one chip and the part of the other circuit, some other part goes into another chip, and they are interconnected across the chip boundaries. This is the intra board, that means within a printed circuit board between chips. Then typically the delays are of the order of 10 times of the basic delay. Similarly, when we talk about 2 different printed circuit boards sitting on the same slot in a system, and they are interconnecting they are communicating among themselves, there the delay can be even more, because the signals will have to go through the back plane back into the another PCB. So, it really depends, just not the partitioning, but exactly at which level you are doing partitioning. The cost of partitioning will depend on that.
So, this delay is delay in the circuit?
Delay in the circuit. There will be capacitive loads and other loads when you are driving off chip. Off chip delays will be much more due to that, because the capacitive and the resistive load will be much more when you are driving some signal outside the chip, just as compared to inside the chip. Yes.
So, by intra-chip, what do you mean here?
Well, intra-chip I am showing a diagram. See, intra-chip means inside the same chip. Suppose we had some kind of a design like this, where we had 3 subsystems A, B and C. Well, we had done some partitioning with this A, B, C being the 3 partitions. Okay. Now, these are the interconnecting lines. Suppose in the initial solution, this diagram shows the initial solution, these are the 2 printed circuit boards, this is PCB 1, this is PCB 2, and inside PCBs these are the different chips, this is chip 1, this is chip 2, now in this PCB this is some other chip, chip 3. So, in this solution, this A, B and C, these 3 sub circuits get mapped into chip 1, chip 2 and chip 3. So, if it is a very big system, I will have to partition it into smaller subsystems, some of them can fit into a chip, some of the chips can fit into a board, and if it is even very big, it has to span across boards. So, suppose a scenario like this occurs. Now, as far as the rough guideline about the delay we just showed, so in this case if A has to communicate with B, there are some interconnecting lines, the cost will be of the order of 10x, because they are across chips. This is intra board, inter chip. Similarly, if it is across boards, the delay is of the order of 20x. But suppose as an alternate solution, suppose another way we had partitioned is that both these subcircuits A and B got mapped within the same chip, say chip I, and the C got mapped into another chip, chip J, but both these were put within the same PCB, PCB K. Then as far as our calculation goes, this A and B interconnection between them will be having a cost of x only, because they will be lying inside the same chip, while B to C will have a cost of 10x. See, this kind of analysis we have to do particularly for the critical nets, the nets which will be ultimately contributing to the total delay of the circuit. So, we will have to try and optimize and minimize the delay of those nets by optimally doing the partitioning. Same is, we have a big design.
The cost of partitioning is only in terms of delay.
Delay of course, and also feasibility. Suppose we are, same as I am giving an example. Suppose we have a big net list, we want to map it finally into FPGAs. Now we know the maximum size of an FPGA, what is the maximum size of a circuit a particular FPGA chip can fit. So we can see that, well, this is the total size of the circuit, I will require 3 FPGA chips to map it. So now the question is that how I will partition the 3 circuits so that they can be mapped into 3 different FPGA chips with minimum performance degradation. So actually when I am doing partitioning, the issue of performance should also be kept into my mind. So if I map into 2 different chips, and if there are some critical nets which are crossing the chips, they will be contributing significantly to the total delay. So I would prefer that the critical nets all lie within the same chip as far as possible. Okay. Fine. So with respect to partitioning, we can now frame the problem slightly formally like this, that we have to partition a big system into subsystems such that the first thing is that interconnection between the partition is minimized, obviously. Now this minimized, this can also involve the costs which I have just mentioned, whether the partitions are getting mapped into the same chip or same board or whatever. So this is captured in the second point, the delay is minimized. Now if you are looking at the same level of hierarchy, delay does not make any sense, but if there are several level of hierarchies like chip, board and system, then this delay makes sense. And if your target, suppose again I am giving that example, if your target is to map a particular partition into say an FPGA chip, this is an FPGA. So a particular FPGA chip will be having a maximum limit to the number of terminals or pins. So the number of terminals of your partition should be less than or equal to that limit. So means if an FPGA chip has 100 pins, you cannot have a partition with 200 pins, and you say that you will have to map it into that chip. So the number of terminals must be less than that predetermined maximum value, and this maximum value will depend on your target. But if it is FPGA, you have a hard limit restriction. If it is an ASIC design, it is more flexible. The area of each partition should remain within specific bounds. Again, for FPGA this is obvious, you have the maximum size of the chip, and even for ASICs there are also some rules of thumbs. You will not want that one particular module or a cell should become beyond a certain size because of design constraints and limitations, other limitations. So normally area bounds are also specified, and the number of partitions may also be one restriction. That means I want to partition it into less than or equal to k partitions, say. But of course this k, you cannot just specify any arbitrary value of k, they will also have to satisfy the other constraints, the size and pin restrictions. Okay, fine. Now broadly speaking, the algorithms that have been proposed for partitioning, they can be broadly classified into three categories: group migration, simulation based and performance driven. Group migration means you already have some groups or partitions defined. Migration means some nodes are moving across the partitions. So, some of these algorithms we have already seen: Kernighan-Lin, fiducia matrices and Goldberg-Bernstein. These are the three methods which fall under this category. Given a net list, you start with an initial partition, say 2, then you try to improve upon this partition. These are all iterative improvement algorithms. There is an iterative loop. In that iterative loop, you try to go and improve upon the partition. There are some other classes of algorithms which are,
Sir, this is
yes,
only if you are doing partitioning into 2. What if you are partitioning into 10 or 12?
10 or 12 we will have to recursively do it, because none of these algorithms can very naturally do a k-way partitioning in general. These are all two-way partitioning algorithms.
So basically this will put one node from this partition into other partition and evaluate the
Yes. Some of them will be exchanging, some of them will be moving a node from one to other. This fiducia matrices algorithm moves a node from one partition to another. Kernighan-Lin, it exchanges two nodes. Well, the other category of algorithm, this is simulation based. In fact, we will see that these simulation based algorithms work very well in with respect to the physical design CAD processes or algorithms. See, in these kind of algorithm, the search space is pretty large, and you cannot optimistically try and obtain the best solution. So, under this circumstances, simulated annealing or simulated evaluation, well, a particular form of simulated evaluation is also called genetic algorithm. So, genetic algorithm is a kind of simulated evaluation. So, these work much better in terms of the quality of solutions you can get with respect to the group migration algorithms. And of course, there is a third category which is performance driven. Well, there you can specify that my total delay has to remain within this, or some you will be specifying some performance related constraints that have to be satisfied. Of course, these methods are much more difficult to satisfy, these constraints are much more difficult to satisfy. They are normally based on certain heuristics which are applied starting with some of the solutions obtained from these. Okay. Starting with a good solution, you try to make some modifications so that the performance you can say the constraints, they are satisfied. But as I told you, they are very difficult to implement in practice. Now, some of the group migration algorithm we have already discussed, but still let us have a quick look at them. This Kernighan-Lin algorithm we had discussed with regards to our discussion with respect to high level synthesis. This we had said that this is a balanced two-way partitioning algorithm, the basic version. Balanced two-way partitioning means given a system, I want to divide it up into two equal halves. If the total size is n, it will be n by 2 and n by 2. And it is an iterative improvement algorithm. In a loop, we try to identify the pair of nodes whose exchange will give me the best benefit, and accordingly I try and exchange such pairs of nodes, right. So, Kernighan-Lin basically starts with a balanced initial partition, and as part of the iteration step, it will go on selecting two nodes, one from this partition, one from the other partition, and exchanging them and evaluate the cost. The pair which gives the best benefit will be selected, and in this way you go on. Okay, fine. And we had mentioned Goldberg-Bernstein is not a separate algorithm in its own right. It uses some properties of graphs. It modifies a graph into another and after that we apply Kernighan-Lin algorithm. It tries to improve the density of the graph. It is seen that Kernighan-Lin algorithm works well for graphs with high densities, but Goldberg-Bernstein algorithm tries to do that and then apply Kernighan-Lin. Well, this fiducia matrices we are not going into detail. This algorithm is slightly different in the way it works. Well, here also you start with two partitions. This can be randomly generated initially, but now the moves are not like exchanging. One particular node can move from one partition to another. So, this can cause or this can lead to partitions of unequal sizes. So, in fiducia matrices algorithm we can have partitions of unequal sizes. Moreover, we can also keep information about multi-pin nets. Multi-pin nets means there may be 3 different pins which have to be interconnected. Normally in the traditional graph we can represent this by either 2 edges or 3 edges, whatever you mean, point to point edges, but we can have so called hyper edges in the generalized graph. So, this fiducia matrices algorithm can also take care of this kind of hyper edges, and all these nodes which are connected by a hyper edge it will try to bring into the same partition. Okay. It means one interesting part of fiducia matrices algorithm is that it uses a very special and efficient data structure to represent the nodes, so that search for the node whose movement or migration will give me the best benefit, that gets reduced. We basically do not have to search much. It maintains some kind of a priority list. The node on the top of that list is the one whose movement will give me the best benefit. So, it tries to maintain a list like that. Fine. So, Kernighan-Lin and its extension Goldberg-Bernstein, they give balanced partition. Fiducious matrices may give non-balanced partitions, unequal. Now, we can extend this basic algorithm. Say for example, Kernighan-Lin algorithm is very simple in concept. Okay. Now, we can extend this Kernighan-Lin algorithm to handle a few other situations. These are the extensions of the basic Kernighan-Lin. The first extension we look at is that we want to have unequal size blocks. So, now what we do, we start with an initial, suppose we have an net list, we start with an initial partition which are unequal in size, with n1 nodes in the first partition, n2 nodes in the second partition. So, we want 2 partitions of size n1 and n2. So, we start with a partition of that size only. So, suppose the initial graph had 2n or 2n vertices, we divide it up into n1 and n2. So, 2n will be equal to n1 plus n2. Now, depending on which is less, which is more, of course, one of the partition will be containing min n1 n2 nodes, other will be containing max n1 n2 nodes. So, if n2 is greater than n1, the first partition will contain n1, second one will contain n2. Now, the way we apply Kernighan-Lin algorithm is the same as we did earlier, but at each iteration we will be exchanging only n1 pair of nodes, assuming n1 is less. Yeah, because in the earlier case, in the traditional algorithm, if there are 2n algorithms, we are dividing them into n and we are iterating till all n pairs of nodes were exchanged, but here we will be stopping with the lower value. Okay. So, apply KL algorithm, but restrict the maximum number of vertices that can be interchanged in one pass to minimum of these two. If n1 is say 10, if n2 is 15, then you exchange 10 pairs of nodes.
That has to be there. Yeah.
That has to be, yeah, the 10 pairs of nodes which gives you the best benefit among these 15. Fine. So, this is one extension you can have to KL algorithm which can handle unequal size blocks, but at the very beginning you will have to a priori mention the sizes. not that depending on your net list you will try to optimally find out what is N1, what is N2, not that. The user will be specifying initially the values of N1 and N2. Okay. Dynamically you cannot find N1 and N2. Okay. Well, in many partitioning cases what happens is that, well, you start with a graph and we assume that all nodes of the graph are equal in terms of complexity or cost, but it may so happen that some nodes may indicate a subcircuit or a module which is bigger than that corresponding to another node. Okay. So, this Kernighan-Lin algorithm can also be extended to that scenario where the sizes of the elements are unequal. So, here what we are looking for is that we still want to partition the circuit into two halves, but now my nodes are not of all same sizes, some are big, some are small, right. Now, let us see how we can represent this in the graph and then you can apply the conventional Kernighan-Lin algorithm. See, looking at the sizes of the nodes, it can be the smallest, it can be slightly bigger, it can be bigger. So, here what we do is that we assume that the smallest node, it has a unit size. Now, with respect to the size of the smallest node, we can assign sizes to the other nodes, say this is 2, this is say 5 and so on. So, assume that the smallest element has a unit size, replace each element of size s with s vertices which are fully connected. Like if there is a node of size 5 say, you replace this node by a 5 node graph, well, each of whose costs are unity, small vertices, and this graph is fully connected. So, you expand this single node into 5 nodes with these edges. Not only that, you also set the cost of these arcs to infinity, all these arcs, so that in any reasonable partitioning algorithm they will all fall into the same partition. Okay. So, replace, yeah. No, it is non-integer multiple. So, the way you are doing it, well, if it is non-integer multiple, even you said that base 2 means half of a node, 0.5 or something like that, just in terms of that you can do. So, you expand it into fully connected, which is called a click, and with edges of infinite width, and then you apply KL algorithm. So, these are some indirect ways in which apply the Kernighan-Lin algorithm to get a solution for these other cases where unequal size partitions or unequal size elements are there.
Can it be a combination of these two?
It can be a combination of these two also, because before applying the Kernighan-Lin algorithm we will have to start with a partition. That partition can be equal, it can be unequal. Yes, true. Okay. So, now let us look at the algorithms which are more widely used because of the quality of solutions they give. These algorithms are probabilistic because they depend on some kind of probabilistic behavior. They are also iterative, there is an iterative loop. So, simulated annealing is a very common algorithm, and simulated evolution is well, it is an extension you can say. As I told you, genetic algorithm is, it also falls under the simulated evolution category. Now, the algorithm of simulated annealing, this is a generalized algorithm framework, this is not a specific algorithm which can be applied to partitioning only. Simulated annealing is a generalized algorithm where there are certain steps of the algorithm which you can modify suitably to apply to any particular domain. Okay. So, we will see how we do it for partitioning. Now, as the name implies, the algorithm of simulated annealing, it tries to simulate the annealing process which is used for metals. normally in metals what happened, you raise the temperature to a very high value, the metal becomes a liquid state, then following a cooling curve you slowly cool down the temperature. So, the metal forms means
Into solid.
depending on whether it is metal or glass, this it either solidifies or crystallizes depending on certain requirements which you want. So, the cooling curve will determine exactly what you want as the final thing. So, the concept is similar, you raise it to a very high temperature, and means at high temperature something random can happen, but as it slowly reaches the freezing point, the mobility of the atoms or the molecules, they get less and less. Okay, so, the idea is like this. So, at high temperature maybe something random is happening, you can go to a worse solution, but as the temperature cools down slowly, the chance of going to a worse solution becomes less. Well, you are basically cooling down to a local minimum kind of a thing.
Yeah.
You are approaching a good solution, towards a good solution you are going. So, the idea is something similar. So, let us see what this simulated annealing looks like. Simulated evaluation we will be looking at later. Well, so here we are talking with respect to our problem domain which we are looking at, the domain of circuit partitioning. So, to start with, we have a random initial partition. This can be generated randomly also. Well, like Carneghan algorithm, we also do some kind of trial exchanges or movement like Fiducious matrices algorithm. So, we make some changes to the partitions, we make some changes and evaluate that what is the quality of the new partition we get, whether it is a better one or a worse one. So, if the quality of partition improves, then the move is always accepted. So, as we move towards a better solution, we always accept it unconditionally. But if we see that the new partition is a worse one, it is not improving, rather it is degrading, still we can accept it with a probability which decreases with the increase in a parameter called temperature, or means it will decrease actually, not increase really. It depends that whether you call it increase or decrease, actually with the temperature it is decrease. So, at higher temperatures the chance of accepting a worse move is higher, at lower temperatures the chance of accepting a worse move is lower. Now, you know how you do this kind of thing randomly in a program. You can generate a random number, say r, in the range of 0 to 1, and if p is your probability, you can check if r is less than p or not. Now, if this is a uniform random number, uniform it means if it follows a uniform distribution, then the probability of any number being generated between 0 and 1 are equally likely. So, if I set somewhere a line p, so the chance of numbers being generated in this area will be having a probability p. So, if r less than p, then do this with probability p. This is how we implement this probability thing in the program. So, with probability p we can do whatever we want in this block. So, we generate a uniform random number between 0 and 1 and check whether that number lies within the probability value specified, then we do whatever we want. Okay. So, means in terms of the annealing curve, okay, well, with respect to the partition, you can call this axis to be the cost, this axis to be the time. So, we normally go from a higher cost to a lower cost, but sometimes we can accept a move with a worse solution. So, sometimes we may move up, sometimes we may move up. So, this moving up may sometimes prevent us from falling into this local minima, come out and go towards a global minima. So, the idea of this accepting worse move is this, that you do not get stuck into a local minima if we strictly follow a greedy approach. Okay. So, this is how we go about doing it. So, now let us look at the simulated annealing algorithm, how this algorithm looks like with respect to partitioning. Well, I am showing you the pseudo code. Fine. In this algorithm, you just look at this T is the temperature. You start with an initial temperature. In terms of the program, this is just a variable. You initialize the variable with some high value, it may be 1000, 10,000, depends on what value. Current partition equal to initial partition. So, you initially generate a partition, this can be randomly generated, and you call it cur part. This can be a structure, this can be anything. I am just in the program, I am just showing it like this. Current partition is the initial partition you have. I compute the cost of the current partition by calling a function called score. Score of current partition will give me the current score. Current score is actually the cost or the goodness of the partition you have. Then there is a repeat loop. In fact, there is a nested repeat loop. So, in the inner loop, what I do? So, I select two parts or two nodes of the graph. These nodes may be selected at random, or these nodes may also be selected based on some heuristics. We will just see these heuristics later. But somehow we are selecting two nodes, one from this partition, one from this partition. This we call them component 1, component 2. And as a trial, we exchange them. Trial partition is obtained by exchanging component 1 and component 2 with respect to the current partition. So, here we get a new partition that we call the trial partition by exchanging these two. We evaluate the cost of the trial partition. This is the trial score. Then we see what is the increase in cost. Delta S equal to trial score minus the current score. This is the increase in cost. If this is negative, it means we are going towards a better solution. Okay. So, after computing delta S, we check if delta S is negative. So, if it is negative, we are moving towards a better solution. So, a better solution is always accepted. So, now the trial score will become the current score, and well, now we are making an actual move. So, means earlier this was just a trial exchange, we are not actually modifying the current partition. See, this you can write in two different ways. This was trial partition. So, either you can write it like this, or you can simply write current partition equal to trial partition. So, either way means the same thing. So, here you are making the actual change to the current partition, but otherwise you are trying to move towards a worst solution. Now, this worst solution you can accept only with a probability that I had mentioned. Now, the probability is computed like this. First, to generate a random number between 0 and 1, this is R, and the probability value here is computed as e to the power minus delta S by the temperature. Now, larger the value of delta S, less will be the probability. So, if you are going towards a very bad solution, the chance of accepting it will be less, but if delta S is less, then this value will be more. So, this is the value of the probability P which I was talking about. So, you check if R is less than this probability value, if so, then you accept it. So, here you accept it. So, the same code out here, otherwise you do not accept it. So, this inner loop is repeated until equilibrium at the current temperature T is reached. Well, now in terms of a practical program, this will mean that the inner loop will be repeated certain n number of times. This n can be 1000, it can be 5000, depends on the application. Again, the number of times you have to repeat the inner loop, that will depend on the problem. Well, it can be lesser, it can be 100 also. So, this is the inner loop. Now, the outer loop now means you recall there are
But
two.
what is exactly equilibrium at T?
Well, equilibrium with respect to the annealing process that is meant.
Yes.
That for a particular temperature you reach the equilibrium, then you again drop the temperature.
So, but here for our case,
Here for our case what we do is that for a particular temperature we carry out a number of exchanges, still we see that we do not get significant improvement anymore. So, we are trying to reach some kind of equilibrium at temperature T, then we again decrease the temperature. So, this particular loop is executed, then we come to the outer loop, this outer repeat loop. This outer repeat loop is actually dropping the temperature. So, the outer repeat loop what it will do, it will multiply the temperature with a parameter alpha which is a number less than 1. So, T will get less. So, until freezing point is reached. Well, in terms of program this can mean until T less than some 0.01 or something maybe. So, you start with the initial temperature, the outer loop will continuously reduce the temperature till it comes below a certain pre-specified value, and the inner loop again is repeated a certain number of times. Now, you can see that an algorithm like this depends on a number of different parameters. Well, of course, how you compute the cost, that may not be very difficult to get, but these moves, how to select the nodes to move, that also for a particular problem you can specify, well, these are the possible moves you can define, you select one of them and make a move. But with respect to the number of iterations you do, the initial temperature you select, the value of alpha, these are all parameters of this algorithm, and for a particular application you will have to do extensive experimentation and fix up those parameters which give you the best result. Now, once you fix up these parameters, you can see that the quality of result you get using these will be much better as compared to Kernighan-Lin, for example. So, in CAT there are many algorithms which are there for this is one partitioning for placement, for routing also. There you use some sort of simulated annealing or some extension of it, and these are actually used in the CAT tools, not just these are they are just used for academic interests.
so because here it can be in one temperature what we are doing, so actually what we are doing in the whole of Kernighan.
In one temperature whatever you are doing in the whole of Kernighan, it is true, but in the Kernighan-Lin we are always following a greedy path. We are always trying to find out the pair of nodes whose exchange gives the best, but here we are not sticking to that restriction. Maybe we are coming out of the global minima. Well,
So we are exploring more of the search.
so Kernighan-Lin will converge much faster, but here we are exploring much more of the search space.
Does this always ensure global minimum?
No, never. This will ensure a good solution in a reasonable amount of time. Global minima, never. No. But I suggest you take a very small application. If you try to code this program, and just you can run and see that how the quality of the solution comes. So just you will get some. You just take some problem which is known to be computationally hard, like the graph coloring problem, for example. You just code it using simulated annealing, run the program and see that how it performs. You will see that you will get a very good solution in a reasonable amount of time.
What is the signal of the ideal equilibrium at T is reached? How do you map it to physical situation?
No, equilibrium T is reached means you are giving some chance for some exchanges to take place at each iteration, because you are just picking up two nodes at random. Well, maybe it is possible that the nodes are such that the cost is increasing and you are not accepting that move at all. So the solutions will not change. So you are giving some chance for the solutions to change.
No, sir. In our case, like T is the delay.
Yes.
Right.
It is a delay means it is the
Temperature in terms of circuit.
huh.
Like delay of the partitioning. Like,
You can say that, yes.
right. At equilibrium T, it means that like we are keeping the delay constant and trying different configurations.
Well, delay you really do not call it a delay. T is more like an iteration. You can say it is the iteration number, some kind of measure of the iterations you are doing. That is the outer loop, So
that
it
delay
is
already calculated in the score.
that is the iteration number, and as the iterations are going on, the value of that p is also decreasing, that value of probability, the e to the power minus delta s by t. So as t is decreasing, that value of e to the power minus delta s by t is also decreasing. So in the future iterations, the chance of accepting a worse move is less.
No, in the inner loop T is constant.
In the inner loop t is constant, yes.
Yeah, you said so probability will remain same.
In the inner loop probability remains same.
What exactly are we doing in the inner loop? Like,
Now inner loop we are trying to make some exchanges. Well, most likely it will lead to a better solution. Sometimes with some probability we can also accept a worse solution. So means we are trying to get a better solution with each inner loop most of the time. That is our objective. But some of the time we can also move to a worse solution, that also we want. We want it consciously so as to come out of the local minimum. Okay.
Does equilibrium at T mean that the current partition has not changed for quite some amount of time?
For the number of iterations, okay, yeah. So this can either be a fixed number of iterations, or the solution is not changing over the last 2 iterations or 3 iterations. Okay, you can do it either way. So in terms of the details, this core function, the way you can compute the cost for partitioning is fairly easy. Say if you have a system where you are partitioning up into 2 subsystems A and B, so you can define a factor called imbalance, size of A minus size of B, magnitude of that. So the difference in the sizes. Well, if your initial objective is to obtain exactly balanced partition, then this imbalance should be 0 ideally. But in some cases it may not be so, where you can accept imbalances which are not 0.
So size in terms of node?
Nodes, well, it depends. If the sizes of the nodes are different, then sum total of those numbers. And similarly cut cost, the number of or the weights of the lines which are crossing the partition, sum of weights of the cut edges.
So this imbalance is used when we want when partitions of equal size.
It depends, because you see that the total cost you can multiply them by some weighted factor W1 and W2, and you can have this cost function. Now if suppose you are starting with a balanced partition, and if you are only using moves which exchange 2 nodes, then the partition will always remain balanced. In that case W1 may be set to 0, because imbalance will never take place. So there you are wholly concentrating on cut cost. So it depends on the situation where you are using, but in some cases you can define some moves where the imbalance may occur. You can move one node from a partition to the other, so the partition sizes may become unequal. So there you can also have to take care of imbalance. Okay. So for the moves you can have again several alternatives. So I told you the simplest is the pairwise exchange. So you can have a pairwise exchange. For this W1 can be set to 0, or you can have it slightly more generalized. Instead of exchanging one element at a time, you can exchange subsets of elements at a time. Say you take 3 from here, 3 from here, exchange them. Okay. Or you can have some kind of an heuristic using which you can select the node to exchange. Like, well, the algorithm like Cunningham-Lin algorithm spends a lot of time to evaluate the nodes, which are the ones to exchange next. But you can make it slightly simpler. Well, you can look, suppose we have these 2 partitions. Well, you can try to find out a node inside a partition which is minimally connected to other nodes inside the same partition, which means that this node really do not belong to this family, you can take it to the other. Or you can try to find out a node where you see that it has lot of connections to the outside. So either which is internally connected to least number of vertices, or whose contribution to external cost is highest. So you can give preference to those nodes for exchange. So it really depends, you can either select the nodes blindly or you can have a little bit of intelligence just put in there, so that you select the node whose exchange can possibly lead to a better thing. So, you can have a combination of this, that means you sometimes you select blindly, sometimes you select this, because if you always select this, again you are trying to follow a path which is greedy, and we are trying to avoid the greedy path. Okay, fine. Okay. So, now let us look at performance driven partitioning. As I told you earlier, that is performance driven partitioning, these are some requirements which come from the user's point of view, and there are no good algorithms which can take care of these restrictions in a very generalized way. Now, these are a few things which you have already mentioned, that the onboard delay is significantly higher than on chip delay. So, typically this on chip delay can be of the order of nanoseconds, and on board delay can be as high as milliseconds, it can be 1000 times higher also, because in that hypothetical example earlier I just showed you 20x, but in practice it can be much higher than that. So, now when you are doing a partitioning, suppose I have a big net list which I am doing a partitioning. Suppose I have partitioned it into 6 pieces. Now, these pieces will be mapped into either a chip or 2 different chips, they may be put on the same board or different boards. Now, it is possible that in this circuit there is a critical path which goes like this. I will have to see that how many times this critical path crosses the partitions.
So, what do you exactly mean by
critical path? Is that path which contributes finally to the speed of operation of the circuit. For example, the maximum clock frequency with which a circuit can operate. There are some paths which, well, if you increase the delay in that path slightly, the clock frequency will go down, but some other parts there is some flexibility, you can add some delay also without hampering the total performance. So, you look at the critical paths, you look at number of times it crosses the boundaries, and means what kind of boundaries they are. So, you try to move things around so that critical path cost gets minimized, and moreover a path which was not critical in the original net list, after partitioning it can become critical because of these added delays. So, this performance driven partitioning has to take care of these things. Okay. So, if a critical path is cut many times, the delay in the path may be too large. So, in case of high performance system, when you do a partitioning, of course, the goal is to reduce the cut size, but also we have to reduce the delay in the critical paths. Now, here the problem is that the definition of the critical path is changing dynamically, as I have just mentioned. So, the initially a path was not the critical path, but after partitioning it is crossing a high cost boundary, so it becomes a critical path. And some timing constraints which are some users, this kind of user level specifications, they have to be satisfied. So, means one way people have approached this problem is that here you can model it as a graph where each vertex represents a component or a gate, each edge represents a connection, the vertices have a weight. In this model, the nodes of the graph will also contain a weight that represents the component delay. If it is a NAND gate, what is the delay of that NAND gate? Each edge has a weight which depends on the partitions to which the edge belongs. If this nodes is connecting to another node, depending on whether they belong to the same partition or different partition, this weight W can vary. So, you model a graph like this and you try to dynamically obtain a good partition, where the total delay will be computed, also taking into account the node delays. So, the problem is very general. As I told you, this is still a topic of intensive research. There are a number of heuristic algorithms which have been proposed, which people use, but there are those algorithms are certainly not very satisfactory, and there are a lot of scopes for improvement. Okay. So, to summarize the partitioning algorithm, we have talked about broadly two classes, group migration and simulation based. To compare them, group migrations take less time, but in general produce partitions which are not of very good quality, but simulation based take longer time, but they give very good solutions. So, in our next class we will be talking about some other step of the physical design process, namely we will be talking about floor planning and pin assignment. Before we can start doing the placement and routing, these are some steps we need to do. Thank you.